Hello, and welcome to another IB Math Speedrun with me, Fitz. Today, we're going to be continuing our graphical exploration of derivatives, so let's jump right in. So, the next thing we need to talk about is points of inflection. What is a point of inflection? It's when a curve changes concavity from concave down to concave up. So, what would be a good example of this? I guess in like an x cubed curve, this point over here would be a point of inflection. So if a function has a point of inflection, say at c, then the second derivative will be equal to 0. And if the second derivative is equal to 0 and f changes concavity through this interval, then this is a point of inflection. So it works both ways. So how do we test if it changes concavity? Well, f is concave down if the second derivative at a point is less than 0, and f is concave up if the second derivative at a point is greater than 0. So if the second derivative changes from negative to positive in an interval, that means that there's a point of inflection. And so that's what we need to find in the following exercises. And just one last thing, if f has a point of inflection at f equals c, and the first derivative is also equal to 0, so the second derivative equals 0 and making it a point of inflection, and the first derivative equals 0, then the point is called a horizontal point of inflection since the gradient is parallel with the x-axis. So we can find those kinds of things on, say, y equals x cubed. So let's jump into some questions. And I guess I'll do the odd ones I'll do the even ones this time. We're doing even today. So for all curves, we need to find points of inflection. We need to find intervals where the curve is concave up. Intervals and concave down intervals. Okay, I can't handwrite, so let's jump into some math questions. So, first let's find, actually I think it would be easier to find concave up and down intervals first. So the first curve is y is x to the 4 minus 3x plus 2. So we need to find the first derivative, dy over dx. And this will be equal to 4x3 minus 3. And then we need to find the second derivative. The second derivative, we notate this as d squared y over dx squared. It's the difference in y squared over the difference in x squared. Sort of. And so this will be equal to 12x squared. So we know that there will there's one point in which the second derivative is equal to 0, and that could potentially be a point of inflection. That's when x itself is equal to 0. So let's test whether this is a point of inflection. So actually no, we don't need to test whether this is a point of inflection. Well, so what we need to do is we need to find the intervals for which this is concave up. And remember, a curve is concave up if the second derivative is greater than 0. And so really for all values in this range, the second derivative is greater than 0. That's the thing. So for when x is part of the real number set, as long as x is not equal to 0, then this is a concave up. And there's no point where this could be concave down, since if we square any value of x, it will be equal to, well, positive, really. So I've lost the exercise. Let me just get back. Okay, yeah. And so there should, I guess, not technically be any points of inflection, because f is concave up throughout the entire domain and it's never concave down. So yeah, there are no points of inflection. So let's move on to the next one. And the next curve is x cubed plus x squared minus 1. So the first derivative is equal to 3x squared plus 2x. And the second derivative is equal to 6x. So in this case, we have a potential point of inflection. Actually, we have a point of inflection at x equals 0. Since when x is below 0, the second derivative will be negative, so this will be concave down. And when x is greater than 0, we will have positive, so it will be concave up. So we have a point of inflection at x equals 0. When x is less than 0, we have concave down. And we have, when x is greater than 0, we have a concave up curve. Whoopsies, I've made a little mistake. I forgot that if we derive 2x, it should actually be equal to 2. So when this will actually be equal to 0 when x is equal to negative 1/3. Oopsies there. So this will be a point of inflection at when x is equal to negative 1/3. So for when all x is less than negative 1/3, we will be concave down, and for all when x is greater than negative 1/3, we have concave up. If you want to look at this graphically, plug it into a graphical calculator, and you'll see the parts below negative 1/3 are concave down, and the parts above are concave up. So yeah, let's move on to the next question. And the next question is, we have x cubed minus 3x squared plus 3x minus 1. Let's get the derivative. dy over dx is equal to 3x squared minus 6x plus 3. And then the second derivative is equal to 6x minus 6. So at this point, we know we have actually a point of inflection at the point x is equal to 1. And so, again, because we're multiplying by 6x, for all points below 1, we should be concave down, and for all points above 1, we should be concave up. Sorry about that. I was very confused because the book gave a different answer to what I put, and the book is wrong. There are questionably many problems with this book, but anyways, let's move on to the final question. And so that's for x to the 4 minus 4x cubed plus 16x minus 16. Well, first of all, let's get the first derivative. It's equal to 4x cubed minus 12x squared plus 16. And then the second derivative will be equal to 12x squared minus 12 times 2, 24x. So we need to find any points of potential concavity. And we can get that by factorizing this, first of all, into 12x times x minus 2. So we have two potential points of concavity. Sorry, I'm back. So I got cut out. So we have two potential points of inflection. And so now we need to check them using, well, by getting points in between them. Those points are, of course, x equals 0 and x equals 2. So let's check the points x is equal to negative 1, x is equal to 1, and x is equal to 3. So when x is equal to negative 1, we have 12 times negative 1 times negative 1 minus 2, which is equal to 12 times 3, or it's positive. So we just need to know x. The second derivative is greater than 0 here. When x equals 1, we have a negative value, and when x equals 3, we have a positive value. As you can see, as we're changing signs, it means that both of these points are indeed points of inflection. So, in between them, where we have x equals 1, we will have a concave down curve, since all of the second derivatives are negative, so this is where we concave down, And outside these boundaries, we have both concave up parts. So when x is less than 0 or x is greater than 2, we have concave up. And when it's between the two, we have concave down. So yeah, that was all for the speedrun. I hope you enjoyed it, and I hope to see you in the next one.